Hello everybody, welcome into another lesson. So today we are going to talk about the limit of absolute value functions and piecewise functions. So here will be the only example of the limit of a basic absolute value function. You have the limit as x approaches -4 of the absolute value of x plus 4. If you just have an absolute value function, well, an absolute value function is defined for the set of all real numbers, so we can use direct substitution. So we can plug in that -4, so this would end up turning into the absolute value of -4 plus 4, which would turn into the absolute value of 0, or simply 0. So the limit as x approaches -4 of this function would in fact be 0. By direct substitution. Now, again, if it's just a basic absolute value function, you can use direct substitution. Where it gets a little hairy is when you have rational absolute value functions, which that's what is going to be the main theme of this lesson. Let's say you were asked to find the limit as x approaches 0 of the absolute value of x divided by x. So you're being asked to find the limit as x approaches 0 of the absolute value of x divided by x. Well, let's first consider something. The absolute value function is in fact a piecewise function. The absolute value of x is equal to -x when x is less than or equal to 0, and then it's equal to +x when x is greater than 0. That piecewise function actually makes up the absolute value function. So, having said that, for one, we can't do direct substitution. You would get 0 over 0, which makes this undefined. What we need to do are consider left-handed and right-handed limits. So first, let's use this piecewise function, and let's take the left-handed limit. So let me write in a different color. So if I take the limit as x approaches 0 from the left of the absolute value of x and divide that by x, well, how do we simplify this? If we're approaching 0 from the left, that means then that x is less than 0. And the absolute value of x behaves as f of x equals -x when x is less than or equal to 0. So we can make this the limit as x approaches 0 from the left of that -x divided by that +x in the denominator. Well, notice now you have the x and the x will factor out. You'll end up just getting the limit as x approaches 0 from the left of -1. Well, the limit as x approaches 0 from the left of -1, the limit of a constant function is just the value of the constant itself. So the left-handed limit goes to -1. Now let's consider the right-handed limit. Let me write in a different color for that. So let's take the limit as x approaches 0 from the right of this function. So the limit as x approaches 0 from the right of the absolute value of x divided by x, well, again, we can't just put in 0 because you'll get 0 over 0. But approaching 0 from the right means that x is greater than 0. When x is greater than 0, this function behaves as f of x equals x. So we can set this equal to the limit as x approaches 0 from the right of +x divided by x. Well, x divided by x will cancel out. You'll get the limit as x approaches 0 from the right of 1. And the limit of a constant is simply that constant. So we got the right-handed limit equals 1, the left-handed limit equals -1. And going back to a few lessons ago when we talked about right-handed and left-handed limits, the only way the general limit can exist is if the left-handed limit matches the right-handed limit, and it does not. So the limit as x approaches 0, the general limit of the absolute value of x divided by x does not exist. So in this case, the general limit does not exist. And let's do another basic example, then we'll get a little bit tougher. Alright, so let's say we want to find the limit as x approaches 2 of the absolute value of x minus 2 divided by x minus 2. Well, we definitely can't use direct substitution because you'll get 0 over 0, so direct substitution's not going to work. Now, notice in the absolute value function you have x minus 2. If you have something other than x inside of the absolute value function, you need to take that and set it equal to 0. X minus 2 equals 0. You'll solve for x. Well, x would equal 2. When you solve for 0, you get what's called your breaking point. X equals 2 is your breaking point. So, what does that breaking point mean? It means that if f of x equals the absolute value of x minus 2, that is a piecewise function defined by the negative of x minus 2 when x is less than or equal to 2. And then it's defined as the positive of x minus 2 when x is greater than 2. So now that you have your breaking point, you solved for your breaking point, you can now treat this as a piecewise function where f of x equals the negative of that x minus 2 when x is less than or equal to 2, and then it's equal to positive of x minus 2 when x is greater than 2. Now we have to consider the right-handed limit and the left-handed limit. So let's take the left-handed limit of this function. So the limit as x approaches 2 from the left of the absolute value of x minus 2 divided by x minus 2. Well, if we're approaching 2 from the left, that means x is less than 2. So that absolute value of x minus 2 would turn into the limit as x approaches 2 from the left of the negative of x minus 2 divided by x minus 2. Now notice between the numerator and denominator, the x minus 2's will cancel out. This would just turn into the limit as x approaches 2 from the left of -1, which would just give you -1. So the left-handed limit of this function is -1. Now let's go ahead and deal with the right-handed limit. So the limit as x approaches 2 from the right of the absolute value of x minus 2 all over x minus 2. Well, okay, if we're approaching 2 from the right, that means x is greater than 2, so this is going to behave as positive x minus 2. So that absolute value of x minus 2, this will become the limit as x approaches 2 from the right of positive x minus 2 divided by x minus 2. And now notice we can cancel out those x minus 2's. You're left with the limit as x approaches 2 from the right of simply 1, which would give you positive 1. So you have a left-handed limit of -1, a right-handed limit of positive 1, And since those two limits don't match, that means the general limit of this function as x approaches 2 of the absolute value of x minus 2 over x minus 2 does not exist. The limit will simply not exist because the left-handed limit does not match the right-handed limit. All right. What do we got next? So let's see here. We have the limit as x approaches 1.5 of 2x squared minus 3x divided by the absolute value of 2x minus 3. So notice that this time the absolute value is in the denominator. Well, first thing you want to do is solve for x equal to, set this 2x minus 3 equal to 0, solve for x and figure out your breaking point. Because we're going to have to define a piecewise function for this absolute value function in the denominator. So if you set 2x minus 3 equal to 0, that's going to then give you that 2x equals 3, where x would equal 3 halves, which we know is 1.5. So you actually have a breaking point at x equals 1.5. So this f of x, let me write this over here a little bit more. So f of x is equal to the absolute value of 2x minus 3. That means we're going to define a piecewise function where it's equal to the negative of that 2x minus 3 when x is less than or equal to 1.5, and then it's equal to the positive of 2x minus 3 when x is greater than 1.5. So now we've defined the piecewise function for this absolute value function. Let's go ahead here and take some left-handed and right-handed limits. So let's go ahead and let's do the limit as x approaches 1.5 from the left of this function. Well, notice the numerator, you can factor out a common x. This will factor into x times the quantity of 2x minus 3 divided by, now if you're approaching 1.5 from the left, what does that mean? That actually means then that you're going to be less than 1.5, so that negative of 2x minus 3 would take over. So you'll take the negative of that 2x minus 3. Well, your 2x minus 3's cancel out. This would end up turning into the limit as x approaches 1.5 from the left of negative x. Well, now you can just do direct substitution, put in that 1.5, you'll get a limit of negative 1.5. That's your left-handed limit. Now, what about exploring the right-handed limit? So let's do the right-handed limit. So the limit as x approaches 1.5 from the right of this function, once again, your numerator is going to have a common x factor out. So you'll have x times 2x minus 3. Divide that by, now the denominator, if you're approaching 1.5 from the right, that means that x is greater than 1.5, so you'll turn that absolute value into the positive of 2x minus 3. So now your 2x minus 3's cancel out. This would simplify into the limit as x approaches 1.5 from the right of x, you can do direct substitution. You'll get a value of 1.5. I should say positive 1.5. Well, the left-handed limit is equal to negative 1.5. The right-handed limit is equal to positive 1.5. Therefore, the general limit doesn't exist. So the limit as x approaches 1.5, the general limit of 2x squared minus 3x divided by the absolute value of 2x minus 3 does not exist. So this limit will not exist. The general limit at least won't. All right, now the next couple of problems are very closely related. So I'm going to go ahead preliminarily and define the absolute value function for f of x equals the absolute value of x as a piecewise function. So that would be equal to negative x when x is less than or equal to 0, and then positive x when x is greater than 0. All right, so what are these next two limit problems? So let's take the limit as x approaches 0 from the left of 1 over x minus the absolute minus 1 over the absolute value of 1 minus x. Okay, well, we need to look at this here. So you just have a general 1 over x minus 1 over the absolute value of x. We want to know the left-handed limit of this function. Well, what does that mean? If we're approaching 0 from the left, x is less than 0, we should probably go ahead and consider that x is less than 0 and convert that absolute value into the negative of x. So this would end up becoming the limit as x approaches 0 from the left of 1 over x. Now, so you'd have minus 1 over negative x. That would turn into plus 1 over positive x. Yes, we can simplify this into the limit as x approaches 0 from the left of 2 over x. Well, here's the thing. If you're inputting numbers closer and closer to 0 from the left, closer and closer to 0, you're going to get closer and closer to negative infinity. So the left-handed limit actually goes to negative infinity. All right, so there's our left-handed limit. Now, they also want to know the right-handed limit for this function. So let's take the right-handed limit as x approaches 0 from the right of this original function 1 over x minus 1 over the absolute value of x. Well, if we're approaching 0 from the right, that means that x is greater than 0. When x is greater than 0, the absolute value behaves as f of x equals x. So this could simplify into the limit as x approaches 0 from the right of this 1 over x. And then if that absolute value of x behaves as regular x, this would be minus 1 over x. Well, notice we have 1 over x minus 1 over x. So this will behave as the limit as x approaches 0 from the right of 0. 0 being the constant, the limit's going to go to 0. So you end up with a right-handed limit of 0, a left-handed limit of negative infinity. So then, if we wanted to now, we could say the general limit as x approaches 0 of 1 over x minus 1 over the absolute value of x does not exist because the left-handed limit does not match the right-handed limit. So I think it's starting to sink in that the moral of the story is that whenever you have a rational absolute value function, the general limit's usually not going to exist. You can get left-handed and right-handed limits, but the general limit's usually not going to exist when you have a rational absolute value function. Alright, now I have a couple piecewise functions, then we'll be done with the lesson. And believe it or not, they're not all that much different than what we've been doing because, again, the absolute value function itself is a piecewise function. We're just going to get into some different things here. So, let's write out the function. So we have a piecewise function here. F of x is equal to 4 minus x squared when x is less than or equal to 2. And then we have x minus 1 when x is greater than 2. So we have f of x equals 4 minus x squared where x is less than or equal to 2. And then we have x minus 1 where x is greater than 2. Alright, now first let's do an easy one here. What if I wanted to take the general limit as x approaches 1? I want to take the limit as x approaches 1 of this function. Well, let's find where 1 is in the domain. We notice that 1 is less than 2, so it's going to behave like the function 4 minus x squared. And 4 minus x squared is a polynomial function, so it's defined for all real numbers. So we can substitute that 1 in. First, why don't we write what the function is that we're taking the limit of. The limit as x approaches 1 of 4 minus x squared. You want to pick the right function, of course, based on your domain and the value you're putting in. Well, we can directly substitute x equals 1 in. That would end up giving us 4 minus that 1 squared, which would end up equaling 4 minus 1, or 3. So the limit as x approaches 1 of this piecewise function is going to be 3. Now, what if I want to take the limit as x approaches 3 of this function? The limit as x approaches 3 of this function. Well, 3 is not at your breaking point. Where you see the x less than or equal to a number or x greater than a number, that number is what's called your breaking point. As long as it's not on the breaking point, which 3 is not, it's fully greater than 2, that means f of x is going to behave like x minus 1. So this will become the limit as x approaches 3 of that x minus 1. And x minus 1 is a linear function, which is defined for the set of all real numbers. So we can do direct substitution. This would be 3 minus 1, which would be 2. So the limit as x approaches 3 of this piecewise function is 2. Now, where it gets really interesting is when you want to find the limit at the breakpoints. So we want to, of course, determine, does the general limit as x approaches 2 of this function exist? Does it exist? Well, if we look to the left of 2, it behaves as 4 minus x squared. If we look to the right of 2, it behaves as x minus 1. So that means if we're going to find the limit right at the break point, we need to do a left-handed and right-handed limit. So let's first take the left-handed limit of this function. So let's take the limit as x approaches 2 from the left of f of x. Well, 2 from the left means it's less than 2, so it's going to behave as 4 minus x squared. So this will become the limit as x approaches 2 from the left of 4 minus x squared. Well, 4 minus x squared is a polynomial function, so we can do direct substitution. So that means we could put in 4 minus that 2 squared. Well, 2 squared is 4. This will be 4 minus 4, which equals 0. So we have a left-handed limit of this function being 0. Now, of course, we need to identify the right-handed limit. So let's take the limit as x approaches 2 from the right of this function. Well, if we're approaching 2 from the right, that means x is greater than 2, so this function is going to behave as x minus 1. So this would turn into the limit as x approaches 2 from the right of this x minus 1. So we can do direct substitution. That's going to then end up giving us 2 minus 1, which is 1. So the left-handed limit of this piecewise function at x equals 2 is 0. The right-handed limit is 1. Well, that means these two limits don't match. That means what we can say is this general limit does not exist. Now, sometimes it will exist at the break points. It does sometimes exist. You have to do your left-handed limits and right-handed limits, and then you can determine if it exists or not. But unlike absolute value functions, or I should say, regular absolute value functions will have a general limit, but rational absolute value functions, the general limit usually doesn't exist. But piecewise functions, your general limit may or may not exist depending upon what you get for your left-handed limit and your right-handed limit. Let's look at another one. We're actually going to do a three-piece piecewise function. So let's say I do h of x. We got h of x is equal to, in three pieces, x when x is less than 0, x squared when 0 is less than or equal to x, which is less than or equal to 2, and then 8 minus x when x is greater than 2. So we have a three-piece piecewise function, and we, of course, we got two breakpoints. You have 0 and 2. Notice how it behaves as x when you have x less than 0. It behaves as x squared when 0 is less than or equal to x, which is less than or equal to 2. And then it behaves as 8 minus x when x is greater than 2. So you have two breakpoints at x equals 0 and x equals 2. Well, let's go ahead here first. Let's try to take the general limit of something less than 0. I'm going to take the general limit as x approaches -1 of this function h of x. Well, -1's not at a breakpoint, so we're good there. -1 is definitely less than 0, so this is going to behave as h of x equals x. So this would be the limit as x approaches -1 of just x. You can do direct substitution. You'll get the limit to be -1. So the limit as x approaches -1 of this function is going to be -1. Now, what if I did the limit as x approaches positive 1? So let's do the limit as x approaches positive 1 of this function, the general limit. Well, is 1 at a breakpoint? No, it's not. 0 and 2 are your two breakpoints. 1's not at a breakpoint, so 1 falls in between 0 and 2, so that means this function is going to behave as h of x equals x squared. So this will become the limit as x approaches 1 of x squared. And we can do direct substitution, so you'll put in that 1 for the x, you get 1 squared, which would give you a general limit of 1 as x approaches 1. Let's do one more regular. Now, let's do the limit as x approaches 3 of h of x. Alright, well, is 3 at a breakpoint? It's not at a breakpoint, so we can fully do the general limit as x equals 3. It's going to exist because 3 is greater than 2, and it's going to behave as h of x equals 8 minus x. So this will turn into the limit as x approaches 3 of 8 minus x. Well, we can do direct substitution, and for x you would get 8 minus 3, which equals 5. So the general limit of this function as x approaches 3 is 5. Now again, where it gets interesting is when you try to find the general limit of a breakpoint. So let's start at 0. Let's see if the general limit as x approaches 0 of this h of x exists. Does it exist? Since you're taking the limit at the breakpoint, at a breaking point, you need to consider the left-handed limit and the right-handed limit. So first, let's go from the left. If we take the limit as x approaches 0 from the left of this function, well, to the left of 0, that means it's going to be less than 0. It's just going to behave as h of x equals x. So this will become the limit as x approaches 0 from the left of x. Well, we can do direct substitution in for x and get 0. So the left-handed limit equals 0. Now we also have to consider the right-handed limit. So let's take the right-handed limit as x approaches 0 of h of x. Well, okay, if we're approaching 0 from the right, that means x is greater than 0, which is going to fall in between the 0 less than or equal to x less than or equal to 2. That means that h of x is going to behave as x squared. So this will become the limit as x approaches 0 from the right of x squared. Well, we can do direct substitution and put that 0 in for x squared. You also get a right-handed limit of 0. So the left-handed limit at 0 is 0. The right-handed limit at 0 is also 0. In this case, the general limit as x approaches 0 of this function does exist, and it's 0. So the general limit of this function as x approaches 0 is actually 0. So this is proof that sometimes you will get a limit, a general limit, depending upon how your piecewise function's defined. Now, the only other limit I would like to do, of course, is at the other breakpoint at x equals 2. This time we want to know, does the general limit as x approaches 2 of this function exist? Well, notice again, 2's at a breakpoint, so we need to take a left-handed limit and a right-handed limit. So let's go ahead with the left-handed limit of this function. So the limit as x approaches 2 from the left of h of x. So if we're approaching 2 from the left, that means x is less than 2. It's going to fall into h of x equals x squared. So this would become the limit as x approaches 2 from the left of this x squared. Well, we can substitute that 2 in for x squared. You'll end up getting 2 squared, which would end up giving you the left-handed limit being 4. So we have a left-handed limit of 4. Now, the other part of this is we have to do the right-handed limit. So if we take the limit as x approaches 2 from the right of h of x, well, if we're approaching 2 from the right, that means x is greater than 2, so it's going to behave like h of x equals 8 minus x. So this will become the limit as x approaches 2 from the right of the quantity 8 minus x. And we can do direct substitution, put 2 in for x. This would become 8 minus 2, which would be 6. So at x equals 2, your left-handed limit is 4, your right-handed limit is 6. Your left-handed limit does not match your right-handed limit, therefore the general limit as x approaches 2 does not exist. So we can say the general limit as x approaches 2 of this function does not exist. Alright, so that's it for this lesson. Next lesson is going to be called the squeeze theorem, also known as the sandwich theorem. So I figured that one might catch your attention, the sandwich theorem. So I hope everybody has a great day. Take care.